Last episode, you learned all 7 major activation functions: sigmoid, tan, ReLU, leaky ReLU, YeLU, GeLU, and swish. You now know what sits between layers. Today, we build the layers.
A single perceptron can't solve XOR. The fix is multiple layers, a multi-layer perceptron, or MLP. This is the architecture that every deep network, every CNN, transformer, and language model is built on top of. By the end of this episode, you'll have a 2-layer MLP forward pass implemented in pure NumPy, and you'll be able to trace every number through the network by hand. I'm Mahaz. Let's build it from scratch. Today, network anatomy, weight matrices, the forward pass with real numbers, function composition, dimension tracking, and a full NumPy implementation. One neuron draws one decision boundary, a straight line. XLAR needs a curved boundary. You can't do that with one line.
The solution Rosenblatt didn't have stack multiple layers. A first hidden layer learns multiple linear boundaries. A second layer combines those boundaries into curved regions. The network learns to carve space into arbitrary shapes. This is the universal approximation theorem. An MLP with at least one hidden layer and a nonlinear activation can approximate any continuous function to arbitrary precision, given enough neurons.
The theorem doesn't tell you how to find the weights. That's backpropagation, which comes next episode. Today we focus entirely on the forward direction. Given weights, how does the network compute an output?
Forward pass first. Always. You can't understand backprop until you fully understand what it's differentiating.
Every feed-forward network has the same 3 types of layers.
The input layer. This is not a real layer. It has no weights, no activation, no computation. It's just the raw input vector x. If your input has 4 features, the input layer has 4 nodes.
Hidden layers. These are the computational layers. Each hidden neuron takes all outputs from the previous layer, applies a weighted sum plus bias, then passes through an activation function. Hidden layers learn the intermediate representations. The output layer. Structure depends on the task. Binary classification, 1 neuron with sigmoid. Multiclass, 1 neuron per class, no activation, softmax applied at lost time. Regression, 1 neuron, no activation at all.
Width is the number of neurons in a layer. Depth is the number of layers. A 2-layer MLP has 1 hidden layer and 1 output layer. Note, people count layers differently. Always clarify whether you're counting weight layers or total layers.
How do layers connect to each other? Weight matrices.
Between every pair of adjacent layers there is a weight matrix W and a bias vector B. If the previous layer has N neurons and the next layer has M neurons, then W is an M by N matrix. M rows, 1 per output neuron, N columns, 1 per input neuron. Each entry W sub ij is the weight from neuron J in the previous layer to neuron I in the current layer. The bias vector B has M entries, 1 per neuron in the current layer. For a 2-layer network with input size 3, hidden size 4, output size 2, W1 is 4 by 3, connecting 3 inputs to 4 hidden neurons. W2 is 2 by 4, connecting 4 hidden to 2 outputs. B1 is shape 4, B2 is shape 2. Total parameters. 4 times 3 plus 4 plus 2 times 4 plus 2 equals 12 plus 4 plus 8 plus 2 equals 26. Every one of these 26 numbers will eventually be updated by backpropagation.
Now let's trace the forward pass step by step with real numbers.
Input x equals the vector 1, 2, 3. Layer 1 weights W1 is a 4 by 3 matrix. Bias B1 is shape 4. Step 1. Compute the pre-activation Z1 equals W1 times X plus B1. This is a matrix vector multiply. Result is shape 4. Step 2. Apply the activation function. A1 equals ReLU of Z1. Every negative entry becomes 0. Every positive entry passes through unchanged. A1 is still shape 4, same as Z1. Step 3. Second layer. Z2 equals W2 times A1 plus B2. W2 is 2 by 4. A1 is shape 4, so Z2 is shape 2. Step 4. Output activation. For regression, output equals Z2. For classification, pass Z2 to softmax or sigmoid. That's it. Input goes in, travels through weighted sums and activations layer by layer. Output comes out the other end. No loops, no recursion, just a sequence of matrix multiplications and element-wise nonlinearities.
There's a clean mathematical way to see what a network does. Function composition.
Each layer is a function. Layer 1 is the function f1 of x equals ReLU of w1x plus b1. Layer 2 is f2 of a equals w2 a plus b2. The whole network is f2 composed with f1, f2 of f1 of x. For a three-layer network, f3 of f2 of f1 of x. Each function transforms the representation of the input into something more useful for the final task. Early layers learn low-level features. Later layers combine them into high-level abstractions. This composition view matters for backpropagation. The chain rule applied to composed functions is exactly what backprop computes. The gradient of the loss with respect to every weight, layer by layer from output to input. Training is optimization over this composed function. The forward pass evaluates f. Backpropagation computes the gradient of the loss with respect to every parameter in f. Gradient descent updates the parameters. Repeat.
Dimension tracking. The number one skill that separates people who debug networks quickly from everyone else.
Rule. If the previous layer outputs shape n and the current layer has m neurons, then w is m by n, b is m, and the output is m. Always write down the shape after every operation before writing the code. For batches, if you pass b examples at once, x is shape b by n, b rows, 1 per example, n columns, 1 per feature. Then z equals x times w transpose plus b is b by m. The batch dimension b just rides along. Common shape check. If you're about to multiply two matrices A times B, the inner dimensions must match. Columns of A must equal rows of B. If they don't, you have a shape bug. This accounts for probably 80% of new network errors. Always print x.shape after every layer when debugging. NumPy and PyTorch tell you exactly where the mismatch is. Don't guess, print.
Before the code, a note on the standard architecture choices you'll see in practice.
Hidden layer activation, ReLU by default. For transformers, ReLU. Never sigmoid or tan in hidden layers of deep feed-forward networks. Vanishing gradients. Output layer activation, depends on the task. Regression, no activation, raw linear output. Binary classification, sigmoid, gives probability between 0 and 1. Multiclass, no activation in the layer, softmax at loss time via cross-entropy loss in PyTorch. Width, for small problems, powers of 2, 64, 128, 256, 512. Starting wider is usually better than starting narrower. You can always prune later. A too narrow bottleneck early in training is hard to recover from. Depth, start with 2 hidden layers. Add depth only if 2 layers genuinely underfits. Deeper is not always better. It's harder to train and more prone to vanishing gradients without residual connections.
Now the implementation. A 2-layer MLP forward pass in pure NumPy, no PyTorch, no AutoGrad.
We define the network as a Python class. The constructor takes input size, hidden size, and output size. It initializes W1 as hidden by input, B1 as hidden, W2 as output by hidden, B2 as output. Weights scaled by 0.01 to keep initial values small. The forward method takes input x, step 1, z1 equals x at w1 transpose plus b1. Step 2, a1 equals maximum of 0 and z1, ReLU. Step 3, z2 equals a1 at w2 transpose plus b2. Return z2. We also store z1, a1, and z2 as instance variables. This is not needed for the forward pass, but it will be essential for backpropagation next episode. Good habit to build now. Test it. Create the network with sizes 3, 4, 2. Create a random input x of shape 1 by 3. Call forward. Print the output shape, should be 1 by 2. Try a batch x of shape 5 by 3. Output should be 5 by 2.
3 shape bugs that trip up nearly everyone building their first MLP.
Bug 1. using W times X instead of X times W transpose. If X is shape B by N and you try W times X where W is M by N, the inner dimensions B and M don't match. Number PY will either crash or silently broadcast incorrectly. Always use X at W.T plus B. Bug 2. 1D input vector instead of 2D batch. If X has shape N, a 1D array, and W is M by N, the matmul might work, but the bias addition behaves differently. Always pass X with shape 1 by N for a single example, never plain N. Bug 3. Wrong output layer activation. Applying sigmoid before cross-entropy loss. We covered this in EP08. Applying softmax in the forward pass, and then using cross-entropy loss. Same problem, double softmax. The output layer of a classifier returns raw logits. The fix. After every forward pass implementation, print the shape of Z1, A1, Z2. Verify each one manually. Takes 30 seconds and saves hours. What changes when you go from 2 layers to 5, or 20, or 100? Mathematically, nothing in the forward pass changes. You just add more steps. Z3 equals W3 times A2 plus B3. A3 equals ReLU of Z3, and so on. Each layer is the same operation. Linear transform, then activation. Practically, 3 things matter more at depth. Weight initialization, random but scaled correctly, otherwise activations explode or vanish. Batch normalization, normalizes activations between layers. Residual connections, skip connections that let gradients flow freely. All 3 get dedicated episodes later in the series. For now, a 2-layer MLP trained with gradient descent on a real dataset is already a fully functional neural network. Not shallow, sufficient for many real problems. The pattern you've just learned, stack of linear plus activation layers, forward pass as composed functions, is exactly how PyTorch's NN sequential works. You just built it manually. Before episode 10, 6 checks. Check 1. You can draw a 2-layer MLP from memory, input nodes, hidden nodes, output nodes, labeled weight matrices. Check 2. You know the shape of W and B between 2 layers of size N and M. Check 3. You can trace a forward pass with real numbers, Z1, A1, Z2, by hand. Check 4. You understand function composition as the clean mathematical view of a network. Check 5. Given layer sizes, you can compute the total parameter count. Check 6. You can implement a 2-layer MLP forward pass in NumPy from memory, class, constructor, forward method. 6 checks. All pass. Episode 10 awaits. Backpropagation. The most important algorithm in all of deep learning. Recap. What you built today. MLP anatomy. Input layer, no weights. Hidden layers, weighted some plus ReLU. Output layer, task-dependent activation. Weight matrix W between layers of size N and M is shape M by N. Forward pass. Z equals WX plus B. A equals ReLU, Z. Repeat per layer. Network as function composition. F underscore L ring operator F underscore 2, ring operator F underscore 1. Always track shapes. Always store Z and A for backprop. Your challenge. Build a 3-layer MLP forward pass in NumPy, sizes 4, 8, 6, 3. Print shapes at every layer. Post your shape outputs in the comments. You just implemented the forward pass of a neural network from scratch. No PyTorch, no Keras, no magic. Matrix multiplications and ReLUs, stacked and composed. Next episode, backpropagation. We take the chain rule, apply it to our composed function, and derive the gradient update for every single weight, from scratch, in NumPy. Subscribe. Build your 3-layer forward pass. Post your shapes. See you in episode 10.